Recall the monotonic convergence theorem for sequences. Any bounded and monotonic sequence has a limit. I will illustrate here using an example the impact of this theorem. Here I will consider a sequence that is iteratively defined. And this is what does it mean? Well, I have a first element. The first element equals 1, and then any consecutive element in the sequence is defined iteratively by calculating 3 minus 1 over the previous element. Yeah, so an plus 1 equals 3 minus 1 over an, and this is true for n equals 1, 2, 3, etc. Yeah, so this defines a sequence. Well, that might be a problem when an for some n equals 1/3, since then the next element would be 0 and then the consecutive element would not be defined. But below you can follow, if you follow what I intend to show, then this already implies that the sequence is well defined. So how am I going to use the monotonic convergence theorem in showing the long-term behavior of this question, of this sequence? Yeah, since the question here is, does the sequence converge? Right? Can we show that convergence of this sequence? Or we might just calculate the first 1,000 elements of this sequence, but it does not per se tell us that it will converge, right? So, and the problem here is that we cannot use the normal limit rules since we don't have any closed formula for this sequence. Okay, so what I will use here is the monotonic convergence theorem, and in particular I will show that the sequence is monotonically increasing. So this means already that from a1 equals 1, there's only higher values. So this already implies that a1 will never be 1/3, right? In case of which we could expect some problems in the definition of this sequence. So when I just prove that this sequence is increasing or monotonic, then we would need that the sequence is bounded, right? So these are the two conditions under which we would, if we add up these properties, then this would show that an is a converging sequence, right? Okay, so there's some work to be done. It's not an automatic thing, right? So we need to prove really something, and that's what we're gonna do in subsequently. So we're gonna prove our first claim, and that claim is that the sequence is increasing. Or we may just calculate the first element. So a1 equals 1, and then a2 is 3 minus 1 over 1 equals 2. And then we might continue, right? The third element would be 3 minus a half is 2.5. So you see that the first elements indicate an increasing sequence. But of course, this is not a proof, right? This requires something more thorough. We're going to use, the technique that we're going to use here is a proof by mathematical induction. So first we define the proposition over the natural numbers, right? So Pn is the statement that an plus 1 is larger than an for all n, and n equals 1, 2, 3, etc. Yeah, notice that this implies exactly that the sequence is strictly increasing or increasing, right? Okay, so mathematical induction requires two steps. First of all, we need to show that the first statement is true, right? So we need to show that P1 is true. Okay, but that is just plugging in the values that we can easily calculate. A2 should be larger than A1, but A2 is 3 minus over A1 equals 2, and this is larger than 1, right? So this is already done. That's the easy step. And the other step that we need to show is that this machinery goes on forever, right? So suppose we know that pk is true for some k, some natural number k, then we need to show that pk is also true in case in the next following integer k plus 1, right? So assume that pk is true for some k. That's how we start, right? And we know that all the earlier statements are also true. Yeah, so we know that we have ak plus 1 is larger than ak, is larger, etc., etc. It's larger than a1 equals 1, right? Okay, what we need to show is that ak plus 2 is larger than ak plus 1. So how can we show it? Well, ak plus 2 is given, right? So ak plus 2 is 3 minus 1 over ak plus 1, right? And I know that ak plus 1 is larger than ak. So if I compare it with the term here, 3 minus ak, then this is a valid inequality, right? Since ak is smaller than ak plus 1, so 1 is divided by a smaller and positive number, and it comes with a minus. So 3, I subtract more from 3 here on this side than I subtract from 3 here on the left hand side, right? And what I obtain here, 3 minus 1 over ak is exactly the definition of ak plus 1, right? That's by definition is this is ak plus 1. So we know that ak plus 2 is larger than ak plus 1, which means that we've shown ak, this proves pk plus 1, right? So, and from the above two steps, p1 is true, and from pk, the pk implies pk plus 1, we have shown by a mathematical induction that pk is true for all k where k is a natural number. And this is exactly what we needed to show. So we know now that an is an increasing sequence. So we are basically done in proving that the sequence converges by showing the second claim, and that is that an is a bounded sequence. Well, an is increasing, so showing that this sequence has an upper bound is enough, right? So in particular, it suffices to show that all the elements are smaller than 3. Yeah, so here again I have a proposition over the natural numbers, and I will show this holds for any number which is a natural number. So why is this true? Okay, again, if we use a proof by mathematical induction, we need to show that the beginning of the sequence Pn is true. So we need to show that P1 is true. So why is this true? Okay, An equals 1, right? So it says 3, but it's 1. It should be 1 here. So that's 1. And that's smaller than 3, of course, right? So the next step is showing that from pk follows pk plus 1. So suppose for all k, right? So suppose now that pk is true. So this means that ak is smaller or equal than 3, right? For some k. Then we need to show that ak plus 1 is also smaller or equal than 3. Okay, but now we have to use the formula. ak plus 1 is constructed from ak as follows, right? 3 minus 1 over ak. But yeah, we know that ak is always larger than 0, right? Since we've shown that this is an increasing sequence starting at 1. So 3 minus 1 over ak is 3 minus something positive, right? So we know that this one is larger or equal than 3, right? Since AK is larger than 0, right? Can you recall why? Can you repeat the reasoning why this is? Well, if so, then we've shown our second claim, because then we know that P1 is true, and we know that from PK follows PK plus 1, and this holds for OK, right? So that means that by mathematical induction, we've also shown that the sequence is bounded. So now we have an increasing and bounded sequence of which we already know that there should be a limit to this sequence. Now the final part consists of calculating the limit of this sequence, right? Since we're just gonna write it down, we know that L equals the limit of n to infinity of an exists, right? By virtue of the monotonic convergence theorem. Yeah, but can we also calculate? Can we calculate this L? Yeah, how we want to do this, right? So, well, let's see what we have. So we need to calculate the limit of n to infinity of an. So the long-term behavior of the sequence is that it goes to L. But okay, but if we let the sequence start with the consecutive element, the next element, so if we, instead of looking at the sequence an, we look at the sequence bn equals an plus 1, then of course it has the same limit, right? Because it's a long-term behavior. So in the sequence an plus 1, we find the same elements as in the sequence an. So if all elements in an are close to L, then in the end, all elements of the sequence an plus 1 will also be close to L. Okay, but now we invoke the the formula that we have of constructing an plus 1. We recover an there, since it's just the limit of 3 minus 1 over an. Yeah, so following the limit rules, we get that it just equals the limit of a constant sequence, which is 3, minus the limit of 1 over an. And if an goes to L, which is unequal to 0, then 1 over an goes to 1 over L. Okay? Yeah, but now realize that on the left-hand side, we started with a limit here. We started with a limit with respect to an, which by definition would be equal to L, right? So that's just the L is the limit of the converging of this converging sequence, right? So now we have L equals 3 minus 1 over L. So we have a direct equation which we might be able to solve. So we're now going to solve L equals 1 plus 1 over 1, 1 over L. So if we multiply on the left and the right hand side by L, we get the equation L squared equals L plus 1, which is an easy quadratic sequence. If we look at this sequence and for the moment forget about the sign of L, we find two solutions in principle, right? So we find the solutions 1 plus minus the square root of 1 plus 4 divided by 2, right? So just use the ABC formula to get these two solutions. So we get, in principle, we can solve for L, and L has two possible values, right? A half plus or minus a half times the square root of 5. Yeah, but of course, a limit is uniquely defined, right? And if you look closely at the values of the solution, we see that 1 is negative, a half minus a half times the square root of 5 is negative, and a half plus a half times the square root of 5 is positive. But of course the limit should be positive, right? So since we have an increasing sequence which starts at 1, we only can go up, right? So we know that L should be positive, right? So we should have a positive value, so we can deduce that L should be equal to a half plus a half square root of 5. That's it.